Today we'll be continuing in physics, talking about the Atwood machine under the effects of friction. This is part 2. We have our same setup of our model of our Atwood machine as before, with each angle shown being pi over 4, with 3 massless strings, and P and Q are also massless. But now we have a weight. We'll call it W0, weight 0, and it has a mass of M0 at the lower end of string S0. Now we also have S2, and we're also going to have another weight hanging from S2. Now we'll call this weight W2, and we'll call its mass M2, and we're asked to find what M2 has to be. Now we want M2 to be the minimum mass that is required in order to have both P and Q remain at rest. So in other words, to have the system remain at equilibrium. So in this case, we'll say that if there wasn't friction, then M0 and M2 would have to be the same since there's no friction. But since there is friction in this case, we start off with putting W0 onto this system. So it has a weight of M0 times G. Once we have W0, then the system is going to want to have W0 fall downwards. So the whole system will sort of move counterclockwise. But in order to prevent that, we have friction, the help of friction, and we also need a certain amount of mass, namely M2. And our goal today is to figure out how much M2 we need. So let's start off by drawing some free body force diagrams on W0 and W2. So let's start off with W0. W0. There are only two forces that are acting on W0. One is the tension from string S0, so we'll call that once again T0, as well as gravity, which acts upon it, since W0 actually does have a mass. So the gravitational force that's acting on W0 is just its mass, M0, times G. Similarly, we on W0, it also has only two forces acting on it, one up and one down. The one going upwards is the tension from string 2, so we'll call it T2 for tension 2, as well as gravity. So gravity is its mass, M2, times G. And since we say that both bodies P and Q need to stay at rest, then the whole system needs to be at rest, which is to say that W0 and W2 also have to have no net forces acting upon them. So looking at these diagrams, we can then conclude that for W0, T0 must be equivalent to M0 times G. And for W2, T2 must be equivalent to M2 times G. So now we want to find a relationship between T0 and T2. So we can start off by also drawing some free body diagrams for P and Q. So for P, we drew the force body diagram in part 1, and we can draw it again for here just for reference. So we have three forces that are acting on body P. We have T1, tension 1, which comes from the string S1, as well as T0, which comes from the string S0. But we also have another force, namely friction. When we just have M0, when we just have W0, the natural inclination of the system is to move counterclockwise. So P's natural inclination is to go down the slope. So friction helps to counteract that. So friction will act upwards, parallel to the slope. So this is our force of friction. And we can decompose T1 into two components again. The one parallel to the slope is T1 times cosine of pi over 4, and the one perpendicular is T1 sine of pi over 4. Similarly, we have T0 T0 can be split into two components. The parallel one we'll call T0 cosine of pi over 4, and the one perpendicular to the surface will become T0 sine of pi over 4. Now the force of friction is equal to the coefficient of friction, namely mu0 times Fn, and we know Fn to be, and here we know Fn to be, well, actually, we can say P actually has 4 forces since we have the normal force on it as well. Right here, the normal force, but we'll just assume that's there. We'll just know that's there because the diagram's getting a little crowded. But we know that the normal force is equal to the two perpendicular components of T0 and T1, so namely T0 plus T1 times sine of pi over 4. Since they both share sine of pi over 4, we can factor that out. Now we can draw a force body diagram for Q, and Q will be very similar to the force body diagram for P. Only, in this case, the two tensions that act on Q are T1 and T2 rather than T0. So we have T1 acting here, and once again we can split it into two components, like so. So the one parallel to the slope is T1 times, this angle is pi over 4, so it's cosine of pi over 4. And the component perpendicular to the slope is T1 times sine of pi over 4. Now another force that is acting upon Q is T2 from string S2. So this is T2. And we can also split it into two components. So the component that is parallel to the slant, oh, this is Q by the way, parallel to the slope is equal to T2. This angle is pi over 4, so it's T2 times cosine of pi over 4. And the component that is perpendicular to the slope is T2 times sine of pi over 4. Like so. Now, once again, we have the force of friction that is going to act upon Q. In this case, the natural inclination of Q is to go upwards the slope, since, once again, the natural inclination of the whole system is to go sort of counterclockwise. So friction is going to act against that, or namely parallel down the slope. So this is our other force of friction. We'll call this first force of friction force 1 and normal force 1. So this is our normal force 1. This is also our normal force 1. All right, squeeze it in there. So this is our friction force 2. And that's also equal to the coefficient of friction times the normal force. But in this case, this normal force is a different normal force, so it's the normal force 2. Now, once again, the normal force N2 is going to be equal to the components of the two tensions acting upon Q that are perpendicular to the slope. So we get, that's T1 plus T2 times sine of pi over 2. Since they have the sine of pi over 2 in common, we can just factor that out. So now that we've drawn a lot of free body force diagrams, we can sort of see to begin what's happening. We've already calculated from part 1 the relationship between T0 and T1 from looking at the free body diagram for P from part 1. So now, if we want to relate T0 to T2, in order to figure out what M2 is in relation to M0, all we have to do is somehow find a relation between T1 and T2. And we can see that T1 and T2 are related by looking at the body Q and its free body diagram. So let's clean this space up a little bit and focus on Q for now. So now we have our free body force diagram of Q from before with the forces T1, T2, the friction force, and the normal force. And I also have in the top right hand corner the relationship between T0 and T1, as well as our goal of trying to connect T0 and T2 in a way in order to figure out the relationship between M0 and M2 and ultimately figure out what M2 is. So now, by looking at Q, our goal is to figure out the relationship between T1 and T2. So we can see that the components of T1 and T2 that are parallel to the slope will be a part of the factors that will figure out whether Q will remain at rest or not. So we can see that the friction force is helping T2 in this case, because it's acting downwards along the slope in the same direction as T2 times cosine of pi over 4. So we want the magnitudes of these two, once summed together, should be equal to the magnitude of T1 times cosine of pi over 4, since that's the only force that's acting upwards along the slope. So if we put that into an equation, we have T1 times cosine of pi over 4 is equal to T2 times cosine plus the force of friction. Now the force of friction, as before, we noted that the force of friction is equal to mu0 times the normal force. And we noted that the normal force was equal to the sum of the components of T1 and T2 that were perpendicular to the slanted surface. Namely, we have sine of pi over 4. We can factor that out since they have those in common, of T1 times T2. So if we plug this into our equation, we have T1 times cosine and T2 times cosine. This part is still the same, but now we replace friction with mu0 times the normal force, which we know to be sine of pi over 4 times T1 plus T2. All that remains is to solve for T2, so let's do that. We have T1, we'll combine the T1s together, so we have minus mu0 times sine pi over 4 times T1, and we know this to be equal to T2 times cosine plus mu0 T2 times sine of pi over 4. Now we want to solve for T2, so we can factor out the T1s and T2s to get T1 is factored out, minus mu0 times sine. This is equal to T2, which is also factored out, times cosine, but this time it's plus mu0 times sine. Then we can conclude that T2 must be equal to T1, and we're going to divide by the coefficient of T2 on both sides to get cosine of pi over 4 minus mu0 sine of pi over 4 over the coefficient of T2, where the only difference is they're added together. The cosine and sine are added together. Now, if we look back at the equation of the relationship between T0 and T1 that we got from part 1, the coefficients look very similar. In fact, they are the same. So once we plug in what T1's relationship between T1 and T0 is, then we get T2 is equal to T0 times the same coefficient squared. Let's see if I can fit it in. So we have the same coefficient, and then we have plus on the bottom, and this whole coefficient is squared. So the whole coefficient is squared. So now that we have this relationship between T0 and T2, we can now solve for what M2 is in relation to M0. So now we have this relationship between T0 and T2. Now we can plug in what we know about T0 and T2 in order to figure out the relationship between M0 and M2. So we know that T2 is equal to M2 times G, and T0 is equal to M0 times G, times this coefficient of cosine minus mu sine over cosine plus mu sine, and over pi over 4, and the coefficient is squared. So now that we have a g on both sides, we can cancel out the g's to get the relationship between m2 and m0. So therefore, we can conclude that m2 is equal to m0 times cosine of pi over 4 minus mu 0 times sine over cosine plus mu 0 times sine, and the whole thing squared. So that is our answer for the relationship between M2 and M0, where M2 is the minimum mass of W2, which is the weight on the right-hand string, in order to keep the whole system at rest.